Welcome to the lectures on evolution of air interface towards 5G. So, we are at present discussing the waveforms for the 4th generation as well as which is applicable to beyond 4th generation, that is the 5G, the foundation for the waveform for 5G, and which is essentially OFDM. So, we have discussed some parts of OFDM in the previous lecture. Let us continue with the discussion on OFDM and see more details about its features, properties and structures, how the transmitter signal flows, what happens at the receiver in this particular lecture. So, in the previous lecture we were discussing about the spectral efficiency that OFDM brings with this particular animation, where we saw that it can give us a huge increase in spectral efficiency. So, clearly there is bandwidth saving and high spectral efficiency. In other words, I mean, you can also think of high spectral efficiency would result in bandwidth saving. So, it can be read in that manner as well. Okay. All right. So, now we see the next picture which is about the orthogonality again, because in OFDM orthogonality is the main thing, and our interest is to visualize, picturize the thing, so that we can even create further things in future. So, what we are trying to see is that in the time domain, how does it look like. So, what we have over here are 3 waveforms, and basically we have 3 different carriers, first, second and the third. So, they are essentially e to the power of j 2 pi f k t, and rather the real part of it, there would be the imaginary part as well. So, we have a real and imaginary, and we are just seeing only one of the parts. So, this is one of the carriers, this is the second carrier, this is the third carrier. So, in the first one we see in this snapshot there is only one fundamental part of the frequency. The second one, which is this black one, we see that there are 2 such cycles. Okay. So, it is an integer multiple of the first one. That is what we are seeing, that it is an integer multiple of the first one, and then we have the third one that we are seeing. There are 4 cycles, 1, 2, 3 and 4, but you can have any other. So, primarily what we are seeing is that there are integer multiples of the fundamental frequency, and if we do the integrals, multiply each one of them, if I multiply this with this throughout and add them up, we will find that the area under the curve goes to 0, and that's going to happen. And one of the reasons that's happening, which is kind of implicit in this picture, is along with these things there is a g of t, which we did not write in the previous slides when we were discussing, but it was already present when we were discussing the fundamental baseline signal model of M-ary FSK, and we discussed orthogonal M-ary FSK, then we discussed the OFDM structure in quite a few lectures back, where we said that let this be the foundation on which we will build, and we had xk in each of the frequencies. So, that means each of these carriers are going to carry a certain x of k, which will be an amplitude and a phase term. So, phase term is going to simply change the starting point, and the amplitude factor will simply change the amplitude. What we see over here is that all of them have the same amplitude. So, this could indicate choice of using a PSK kind of a structure or a QPSK kind of a structure that could be imagined to be associated with this particular waveform. Okay. So, essentially what it means is that if we have integer number of cycles of the fundamental frequency, then they would be cancelling out each other when you are processing at the receiver side, and one would get orthogonality, and this is the corresponding time domain picture of whatever we have seen in the frequency domain. So, this GT, that is what we were seeing. This GT, if it is rectangular, this is very, very important. Rectangular means that it is constant over this entire period. Then only we get the result of orthogonality, which we have discussed earlier, this result. Okay, because you can clearly see in this orthogonality picture equation, we should have had a GT along with a G conjugate of T, right. Now, if these equations or if these expressions were kind of let us say a raised cosine, then the condition of orthogonality would be different. So, this is some important thing which we should keep in mind, that has been implicitly present in this, and we may not have mentioned this explicitly, but that is what we should remember. Now, if we change this GT, orthogonality criteria breaks down within this 1 by T criteria, and it will be some other condition on which we get orthogonality, or it will depend on the choice of GT as well. And when we said that we will get some opportunity to discuss some of the futuristic waveforms, people have already worked on them. One of the fundamental things that people have been thinking or spending their time upon is the pulse shape, or GT, along with this multicarrier. So, these two things together have been investigated. We will get an opportunity later on to look at them. So, primarily this integer number of cycles of each subcarrier is present, which is giving the orthogonality, and this is how one should look at it when one sees the time domain picture. So, this orthogonality expression we have already discussed this, where here this f12 and f2t are chosen in a manner that they are the basis functions. That is what we have said. That means, each one of them is e to the power of j 2 pi, let us say f1 of t, and this is let us say e to the power of j 2 pi f2 t, right. And if one would like to bring in g of t over here and g of t over here, then one would find the orthogonality criteria using the entire GT as well, and one could think of using a certain GT g1 of t over here, a certain g2 of t of in the second one, which is a more generic way of doing things, and we will see some of the outcomes at a later stage, but which is not relevant for 4G or 5G, but potentially important for the future generation works. Okay. So, yeah, I mean, as we have discussed, that the area under the region would be 0 if they are different, and if they are the projection of 1, or only if they are equal to each other, then it will be non-zero, right. So, this also we have discussed that in Ofdm the frequencies are chosen so that they are mutually orthogonal, but I will always remind you to recall that we have chosen GT to be 1 in all the expressions, then only we have got this criteria, otherwise the result changes. This remains constant for all the Ofdm. All discussions that we think of Ofdm would be valid only with GT is equal to rectangular, or not changing within the period of interest. Now, one may think of a question about that how would one think of windowing. We will discuss windowing. Some people already know about windowing at this stage. So, there is a cyclic prefix which we will also discuss. So, over the period of interest is a short discussion before we go into finally there. In the period of interest where we are actually doing the processing, you will find that the pulse amplitude remains constant. So, if we are interested in this particular section, over that period we can assume a rectangular shape, and the spectrum that we have considered to be sync in all the discussions that we have had is primarily because of having considered a rectangular pulse shape. All right, moving ahead. So, some other important aspects of Ofdm, why it is used for wireless communication, is that it is well known for effectively combating the frequency selective fading. Now, this is very, very critical, and frequency selective fading which occurs due to multipath reflection. So, we have discussed earlier when we were talking about the rake receiver, that if there is a transmitter and a receiver. So, let us say this is the transmitter and this is the receiver, and there are reflectors all around the place. So, the signal from the transmitter to the receiver would go via multiple paths, right. It will come via multiple paths, and if you send an impulse from the transmitter. So, let us take another color. So, if I would send an impulse from the transmitter, which is kind of delta t, what we will find at the receiver is, if we draw this as the timeline and this as the received signal power or amplitude, the first path, we have discussed this thing, but we are doing it in short, is kind of arriving after a certain propagation delay corresponding to the delay of the first path, then of the second path, third path, fourth path, and so on and so forth. So, effectively the impulse gets spreaded in time, right. So, when things get spread in time, things in the frequency domain would get restricted or shorted. So, if you look at the Fourier transform of the delta function, it is kind of flat in frequency. Flat means it is the constant value across the entire range of frequencies. But if we take Fourier transform of such a sequence, and of course, there will be a phase associated with each of these pulses, we will find that the frequency response in the frequency axis will not be flat. This is flat in case of a delta function, the Fourier transform would be flat, but here what you will find is that the frequency response would be fluctuating something like this. We will see those pictures. So, in OFDM we will again have a picture of that when we are seeing these narrow subcarriers, there is a design issue involved. One usually chooses it in such a manner that the bandwidth of the carrier is such that it experiences near flat fading. So, that is what it means, that it is kind of very resilient to frequency selective fading. So, that is in short about the discussions we will see again later on. So, one needs to understand the propagation characteristics very well in order to understand what the frequency selectivity and the multipath and how does OFDM take care of it. So, if it experiences a flat, that means nearly flat frequency response, equalization is easier. So, that is again a huge advantage for wireless communications, because already you have a lot of extra complexities. This is going to only help reduce the complexity that is to be addressed. Okay. So, so this way we will proceed towards studying the architecture of the transmitter. Now, that is one of the objectives, but before we get into that, it is important to look at the signal model, which will again help us in realizing the transmitter architecture. So, we have already written this kind of a expression before. So, x s of k, k is the subcarrier index, okay. This is the subcarrier index which we have been writing, again which is being reflected over here. So, what you see in this particular part is that you have k multiplied by 1 upon T f, and T f is the same as T as we have used in the previous slides. Okay. So, wherever you have used T, it is actually T f, where T f is the duration of the OFDM symbol, right, and T f is equal to T, whatever we have done is equal to 1 upon delta f, and delta f is equal to f k minus f k minus 1. Okay. So, that completes the definition, and what you see is that k multiplied by this is effectively this expression is basically k multiplied by delta f. Okay. That is the frequency separation. So, if k is equal to 0, you have the DC carrier, if k is equal to 1, you have the first fundamental frequency, and so on. All right. And all of them are appearing simultaneously. So, therefore, there is a summation and there is a normalizing factor. This normalizing factor one can either consider or one need not consider this, it depends upon one's choice, because this is not going to matter finally except in mathematical notation, because if you are actually realizing a system, you would usually normalize the power to a certain desired value and you will send it out. Only for mathematical convenience, this kind of normalization factor is used, so that one can get the normalized power of x s of t as 1. The x capital X s of t, which is the constellation, can also be normalized to a unit power. So, this normalization is something which depends upon your actual realization and if you are doing simulations, otherwise it is kind of okay. All right. So, these are all the things that have been described over here. Amongst these, one should pay attention to this function, which is the gating pulse or our g of t minus STS. This is basically the gating pulse. S is the OFDM symbol index and Ts is equal to Tgi, which is the guard interval, which we will talk about, plus Tf. Okay. So, we have over here certain other offset values. So, these offset values are present in order to create the signal in an appropriate manner. We are not going into the exact details of opening up the equation, but I can leave it as an exercise for you to work out the details of it and understand what is the meaning of this. We will see that x t, which is a summation over x s, it is a summation over x of s. Okay. So, what is the meaning of this in this particular expression? We see that g t is essentially an expression which is like this, that means it is rectangular over a period of T s, okay. And T s we said is equal to T f plus T g I. So, that means if we say that this duration is the duration of T f, okay, which is equal to 1 upon delta f, right. T s is actually larger than that, and the extra portion is the cyclic prefix, and now one can easily see that we can have some shaping over here and some shaping at the end without affecting the rectangularness in within the region of our consideration. Okay. All right. So, we will discuss again some more things there. So, this essentially helps us in writing this notation over here, whereby we have like the first Waveform symbols pulse shape, the second Waveform symbols pulse shape, and then the third Waveform symbols pulse shape, then the fourth Waveform symbols pulse shape, and so on. So, these are all orthogonal to each other in that sense. So, although it appears like a summation, but it is actually a sequence. So, these are again some things of notation which one should remember to use appropriately, so that things do not get mixed up. So, now we look into the transmitter structure. It is very important to understand the structure, because this is something which will be used throughout. So, there are binary input bits which are coming in at this point, and these binary bits are a sequence of zeros and ones which are converted from serial to parallel. Now, why is it done so will be clear once we look at it. So, here if we look at the output of OFDM, what we have is x k e to the power of j 2 pi f k t, right. So, and there are some over all these different subcarriers. So, we just take a look at this expression. So, these are the constellations and these are the carriers, all right. So, that is what we have over here, and these are happening in parallel, that is why we have this kind of a summation. Okay. So, now what we should see is that each of these subcarriers should be loaded simultaneously, right. So, if they are to loaded simultaneously, these ones 1, 2 up to n are the different subcarriers. We had said that this summation, this thing would be realized as a DFT. So, now for clarity, if you look at this particular expression, we can clear all the markings that has been put on this particular slide, okay, and things will be easier now. Okay. So, if we look at this t is continuous time. We can change this continuous time into sample time, where let us say t samp, where t samp is the sampling period and t is the time where it is equal to n times t sampling. Okay. So, if that is so, we can realize this entire thing in the discrete domain, in the digital domain with index n. So, instead of putting t, we can index this as n, and here instead of putting t, we will be again indexing this as n, and this T f will be some multiple of this T samp. Okay. So, effectively when we look at this particular expression, one will be getting x k, sorry, the notation sth OFDM symbols kth subcarrier e to the power of j 2 pi. Okay. So, now n multiplied by t samp. So, we have this 2 pi of course, then k multiplied by 1 upon n times T S M P, and you have the T part which is n times T S M P. I am just only taking this particular T. These offsets I am kind of neglecting as of now in order to understand these offsets I am neglecting. So, one can of course, bring them back, it is not going to affect your expression. So, this cancels out, you have a summation over k and you are going to have x of n. So, now if you look at this expression, it is simply x s of k e to the power of j 2 pi k n upon n sum over k. This is nothing but the DFT which can be realized through an IFFT expression, and this is what we have as x of n. Okay. So, that means this entire thing can be realized in a complete discrete manner, and entire set of multiplication operation that was happening here could be replaced by a multiplication, and this summation, this huge processing can be simply replaced by a DFT, and the DFT can be also replaced by an IFFT operation, because IFFT is very low complex, right. So, we have to now visualize this entire expression that is happening over here through the view of IFFT, right. So, that means in IFFT all these xk's, these are the inputs of the IFFT. So, we change the pen color to mark it better. So, these are the inputs, right. So, we have xk's as the inputs and xn's as the outputs, and in between we have IFFT, right. Through IFFT it produces this time domain. So, now why we call it IFFT? Of course, there is a direct similarity, and then what we see is that these were actually modulating the frequency as the subcarriers, and this is the time domain signal. Although this is the common way of explaining such things, one can even visualize the entire thing as time domain operation, but since there is a huge similarity with IFFT, one can take frequency domain as input and time domain as output. That is also another way of viewing things. So, whatever way is comfortable, you can see that end of the day one has to ensure, or one knows that it is finally a time domain signal that is one is handling with. But more popular description is that this is the frequency domain and this is the time domain, and that is how you will find in most of the notations in most of the discussions. Okay. So, now we are back to the transmitter structure. So, what we see is that each of these are the index of the subcarriers. So, they must be filled with these different constellations. So, here it is x n. So, rather as per the notation in this particular slide, it is 1, and s we are kind of is equal to 1, or we are kind of omitting s. You are omitting s for ease. So, we are just noting the subcarriers for this one particular Ofdm symbol, and symbol mapping can be anything depending upon the signaling from higher layers or the choice, and as said the symbol mapping can be different in different subcarriers. So, now if we are using 64 QAM, this would be having 6 bits. If let us say we are using 64 QAM in all, they will be all having 6 bits, and if the value of n is let us say 1024. So, you will be sending 1024 multiplied by 6 bits simultaneously, correct. So, so many bits from here 1024 multiplied by 6 bits have to be read, and they have to be sent 6 bits to each of the branches, and there will be 1, 2 up to 1024 such branches. They will be doing a symbol mapping feeding into IFFT, and here we are going to get the output small x of 1, small x of 2 up to small x of n minus 1, and finally, we are going to get small x of capital N, n number of samples. Then we will be reading them out in a manner x 1, x 2 up to x capital N, and they will go out to the analog section. Of course, there is an addition of cyclic prefix, we will discuss the addition of cyclic prefix, and it goes to the analog part and then to the RF chain. So, this is how the signal flows, and the equations that we have written maps to this kind of a structure. So, moving ahead, what we see is that there are some critical parameters. One of the parameter is the subcarrier bandwidth, that is or subcarrier spacing. Sometimes it is also called the subcarrier bandwidth, okay. And the other parameter is the guard interval, which we will discuss. Sometimes or most of the time it is also called cyclic prefix. So, guard interval is a more generic term, cyclic prefix is a very specific implementation of the guard interval, and one would remember that this subcarrier spacing, which is effectively or essentially written as 1 by delta f, sorry it is delta f, one could rather specify it by delta FSC indicating subcarrier spacing, and this was equal to 1 by T or 1 by TF, whatever is the notation we have been using. So, that means one chooses the subcarrier spacing, the symbol duration gets decided. This is very important to understand, and there is also another thing, the guard interval. Now, why we are saying that these are important parameters? For two reasons or multiple reasons. One is that this is the diagrammatic representation of a channel impulse response. Now, in a typical single carrier system if it has a certain amount of bandwidth, the pulse duration, which is indicated over here, clearly there is inter symbol interference, because the echo is larger, whatever symbol is being sent in this part gets stretched to this part and to this part. So, there is ISI. Okay. So, in OFDM what we are doing is that the symbol duration is usually made large, and this is that T, which is equal to TF in the notations that we have been using till now. I am just warning that we will probably have some change of notation later on, okay, is made large enough so that this channel impulse response CIR length is much smaller than T, or T is much larger than channel impulse response. Okay. So, we said at some point that these subcarriers, individual subcarriers, their width should be decided in such a manner that they are smaller, pretty much small, so that it experiences nearly flat fading. Now, we have to go into the details of propagation characteristics, which we will do later on, that these two are highly interconnected. Now, a flat fading effectively means that the channel impulse response is perceived as an impulse. It is not a stretched version of the impulse response. It is not a stretched version of the impulse. That means, echoes are not present. So, to allow echoes to vanish, one has to make this T sufficiently large. Now, although you make T sufficiently large, what you will find is that end of it will still stretch, and there has to be a next symbol that comes in. So, basically this is one OFDM symbol, you have made it pretty large compared to channel impulse response, this has already been made, but still because of the channel impulse response, this will become, the end will become something like this. Now, the next OFDM symbol is supposed to start from this point. So, there will be some amount of ISI which is present over here. Okay. To avoid that, what one can usually do is one can choose a design where the symbol duration, whatever is present, and the next symbol there is some guard interval. So, we are using the term interval instead of band over here, right. So, this is the beginning point, this is the end point, okay, for small n, and one can see it, I mean that means there is this guard interval between the two. What is done is this signals which is coming afterwards, they put some kind of information which we will see what is called the cyclic prefix, but effectively there is a filler or a gap between these two signals. So, this channel impulse response is going to die out over here. If it dies out over here, there is ISI free system and one can have the communication. Now, one can argue that one can design a orthogonal system in time like one have designed an orthogonal system in frequency, but we must be very careful at this point to note that when we designed the orthogonality in frequency or orthogonality within a symbol, we had used integrate 0 to t e to the power of j 2 pi f c t e to the power of minus j 2 pi f k t f k prime t d t, correct. We did not have any other thing in between, but now what we have is the channel impulse response. So, orthogonality can be brought in if we bring this channel impulse response into the picture. If we bring this channel impulse response into the picture, then we must also have a convolution with the channel impulse response as the basic signal, and overall we can bring in an orthogonality, but that would mean that this channel impulse response information is required at the transmitter. It requires to be available at the transmitter. So, that being made available and then being used kind of makes things very difficult. That is one of the aspects. So, we cannot avoid it, and hence it is better to choose a guard interval, a loss which you can't help, but then there are mechanisms which people have been working on to reduce this guard interval. We will get an opportunity to see that. And now, coming back to the other important thing, if we make this t very long, then because of mobility there is a factor called Doppler which comes into play, which we will see again later. Because of Doppler or because of mobility, we have said that channel fluctuates in time. We also require that the channel remains constant in this entire period. Okay. So, that means t, our symbol duration, must be smaller than something known as the coherence time of the channel, and this subcarrier spacing delta f must be less than the coherence bandwidth, that means the bandwidth across which the channel remains flat. So, these are the two important conditions that are required to be satisfied. Now, delta f, as you can see, it is equal to 1 by t, which is from this, and this is another condition. So, we have two conditions over here, 1 by t must be less than coherence bandwidth and t must be less than T c, or 1 by t must be less than 1 upon T c. So, these two conditions have to be satisfied simultaneously in order to make the system work, as well as the other thing which is the T g I, which we have been referring to while looking at the equations. So, now this is clearer. T g I should be greater than the maximum channel impulse response length, or tau max as we call it. So, tau max is the maximum length of the channel impulse response. In this picture it is tau max over here. So, this is the third important condition that one should consider. So, one, let us change the color of the pen. So, this is first condition, this is the second condition, this is the third condition that one must keep in mind while designing such a system. So, we stop this particular lecture over here, and we will continue more on the fundamentals of OFDM in future lectures, because based on this, as we have been saying, the fourth generation system stands, the fifth generation system stands. So, it is essential that we understand it thoroughly, so that things become easy whenever we discuss the air interface for the next generation systems. And it is although kind of not required to mention, but we should see that OFDM in the wireless system has been popular over last 2 decades. It has been used even beyond that. It is going to be there for another decade. So, it is going to live for a very long period compared to the history of wireless communications. So, it is essential that we understand the details, and we hope that with this you will be able to design future things, improve upon this basic structure that exists to an extent that we can have even more advanced system in future. Thank you.